So here's the next part of confidence intervals. Now that we have completed confidence intervals with a population standard deviation, our next section is doing it when we don't have a population standard deviation. So in this next section, this is when you are given a sample standard deviation, which is your variable lowercase s. And for those types of problems, we're going to use a different distribution. So this whole next section is all about t-distribution. So the first thing we need to do is kind of define t-distribution. Previously, we've talked about normal distribution, which sometimes on shorthand we just call z-distribution. This is t. So this is when your population standard deviation is unknown, your sample size is less than 30, and the random variable is approximately normal distributed. So it would follow a t-distribution. Now you'll notice here, this is the same as your z-distribution, z-score formula. Just for reference. Same thing. The only thing we changed in it was our symbol for standard deviation. So it's not very different. What is going to be different is your critical values. Your critical values are now going to be denoted by a t with the subscript c, and we're going to find them by using the function in your calculator called inverse t. So a few properties for your t-distribution. You still have the mean, median, mode all equal to 0 in the middle. We are still bell-shaped and symmetric. So I'll make a little sketch for you to see. The total area under the curve is still 1. The big thing that starts to change with this to be different than our normal curve is that there are numerous curves and the tails are thicker on the ends. So they're a little higher off the number line on the end. Your standard deviation of your t-distribution varies with your sample size. So sample size is going to affect our critical values. It is a family of curves. So there are numerous curves. Each one is designated by the degrees of freedom for it. So it is the number of free choices left after a sample statistic is calculated. So to find our degrees of freedom, which will be asked for when you use inverse t in your calculator, it is always n minus 1. So whatever your sample size is, less 1. You can think of it as there's one less person who has the freedom of choice as each person is like, for example, going into a classroom. Each student grabs a chair as they fill in, but it's that last student who walks in the door who doesn't have freedom. They just have to pick that last chair that's open in the room to sit in. So it is n minus 1 is your degrees of freedom. It's the number of free choices left. So here's a nice little image of the family of curves. This is just 3 of them. Your blue line is your standard normal curve, and then we've got 2 additional ones on here. Notice how they're thicker on the ends. And because they are thicker on the ends, the middle is a little bit less tall because the whole area under the curve still has to add up to 1. Anytime you have degrees of freedom of 30 or more, it is very close to that standard normal. So as your degrees of freedom get higher, the closer you get to that blue line. Now that we've talked about the properties, let's try one. So this problem says find the critical value TC. So that's a clue to let you know that you're using inverse T here for a 95% confidence when your sample size is 15. So just like we've done before, confidence is 95%. So we can write that as 0.95. Before we plug it into our calculator, we're going to do 1/2, 1 minus C. So 1/2, 1 minus that 0.95. This is helping you find the area under the curve and your tails. So if 95% in the middle, that leaves 5% for your tails. And since they're symmetric, we cut it in half. So 2.5% in each tail. That's what this number is, just as the decimal. These are the same. So then in our calculator, we can do inverse t, plug in 0.025. This is going in for the area spot. Then for degrees of freedom, it's n minus 1. So your sample size, your n is 15. So your degrees of freedom is 15 minus 1, or 14. So we type in our area, our degrees of freedom, we click enter, and we get our TC. Your calculator will show it negative, but it's both positive and negative of that number, 2.1448. And again, for this whole PowerPoint, we are using 4 decimals for each one of our answers. So we have rounded this off to 4 decimals. That is your critical value. So going through the motions of finding a confidence interval when we don't have that population standard deviation, again, you will be given the S symbol, or it will say the sample standard deviation, or it'll give you other clues like mentioning TC or using the T distribution. So again, it should either be normally distributed or it'll have a sample size bigger than 30, but most of these will say normally distributed. Find the sample mean if they give you the data set, otherwise that might be given to you. Then we're going to use degrees of freedom and inverse T to find your critical value. Margin of error formula is the exact same as the last section. We've just changed the symbol for critical value and standard deviation for the new section. And then just as your reminder, your interval at the end is going to be the parentheses interval. So your sample mean minus E and your sample mean plus E. That's how you're going to write your final answer for the confidence. So here we go. Let's try it. You randomly select 16 coffee shops and measure the temperature of the coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold. Assume the temperatures are approximately normally distributed. So I always recommend you read the whole problem first. And the clue to know that this is going to be a T distribution is right here. Sample standard deviation. Always look for your standard deviation. If they give you a population standard deviation, you use Z. If they give you a sample, you use T. That's super important. That's how you know the difference between the last section and this one. So let's see what else they give us. We've got 16 as our sample size. They do give us our sample mean. We have our standard deviation. 95% is our confidence. And again, notice it does mention that it's been randomly selected and it was normally distributed. So here's a little bit more space so we can solve through all 3 of our steps. Find the critical value, margin of error, and then confidence interval. So the first one, critical value. We had 95%. So plug it into our formula. This is going to be for our area, 0.025. So inverse T, we put that in for area. We also need to put in our degrees of freedom. So just as a reminder, our sample size is 16. We need to do n minus 1 for degrees of freedom. So we should be plugging in 15. When you click enter or calculate, we need both the plus or minus of that number, 2.1314. This is our critical value. Once we have critical value, we can find the margin of error. So we plug in always the positive of our critical value. Our standard deviation was 10, and our sample size was 16. So margin of error should always come out positive, 5.3285. This is your margin of error. And your last step for your confidence interval is finding those endpoints. So taking our sample mean, 162, minus our margin of error, and then repeat the same thing with an addition in there, adding the two numbers together. So this would be your final answer, your confidence interval. So let's try another one. This one says you randomly select 36 cars of the same model that were sold at a car dealership and determine the number of days each car sat on the dealership's lot before it was sold. The sample mean is 9.75 days with a sample standard deviation of 2.39 days. Construct a 99% confidence interval for the population mean number of days the car model sits on the dealership's lot. So again, when we mix them all up, first thing you should look for is the term standard deviation. And right in front of it, it tells you that we have a sample standard deviation. That means this is all going to be a t distribution. That's what we're looking for. So then we've got our sample size, 36. We have our sample mean, that's x bar. We have our S for sample standard deviation. We have our confidence, 99%. In this case, our sample size was bigger than 30, so we don't need it to say normally distributed if it's big enough. And it does say random. So let's go through those motions. Critical value. Confidence is 99%. Switch that to a decimal. Plug that in. Keep in mind when we're plugging it into the 1/2 1 minus c, you don't have to use that formula if you want to just think it through. If 99% is in the middle, we have 1% left over, but we have two tails, so you got to cut it in half. So this is a 0.5% in each tail. It's nice when you use the little formula though, because it does give you that number already switched into decimal form, which is exactly what you need when you plug it into inverse t. So that goes in for area. Degrees of freedom, our in was 36. So we're going to plug in 35 because that is in minus 1 to get that value. So our TC is both the positive and the negative of 2.7238. That is your critical value. It is very helpful to name all of these pieces as you find them. So when you are asked specifically for different parts, you know which part goes where. A lot of the problems, we're trying to get you all the way to that end, but some questions will only ask for critical value or only ask for margin of error. So making sure you know how to get to each of those individual numbers is important. And then our next step is finding that margin of error piece. So we've got our formula. Plug in the positive critical value, our standard deviation over the square root of our sample size. We solve and get 1.0850 when we round it off to 4 decimals. This is your margin of error. And then our last step is taking that and adding it and subtracting it from our mean. So in this case, our mean was 9.75. Add and subtract it. And we have our confidence interval. Now again, when you're trying to figure out if something is going to be normal or Z distribution or the T distribution, you are looking for primarily your standard deviation. So the first thing you do is if you have it say normally distributed, or if your sample size is bigger than 30, that's bare minimum to do any confidence interval at all. If you don't have that and you say no, you don't have it, you can't use either. You cannot use either of the two. You can't use Z, you can't use T. So it always has to say normal distribution, or it has to be a sample size bigger than 30 to even proceed. Once you have that, then you're really asking yourself, what kind of standard deviation do you have? That's the big clue. So if you have population standard deviation, and again, your symbol is that lowercase sigma, you use Z. If you have sample standard deviation, or if it doesn't say, and it just says standard deviation, nothing about population or sample, then you use T. You also might see the lowercase s for sample. So on this last one for this section, it's just asking you to figure out whether it would be normal or T. This problem says you randomly select 25 newly constructed houses. The sample mean construction cost is 181,000. The population standard deviation is 28,000. Assuming construction costs are normally distributed, should you use the normal distribution, the T distribution, or neither to construct a 95% confidence interval for the population mean construction costs? Explain your reasoning. So first things first, it does say normally distributed. It's either that or sample size had to be bigger than 30. So we do have that. Then the next thing we notice is the population standard deviation. So this is a normal, sometimes we call it a Z distribution, because you're given that population standard deviation. That's the big one. Now, the last section for chapter 6 we're going to cover is a third distribution piece. So we either have things that are Z or T based on the type of standard deviation. But in this last section, there are no standard deviations and there are no means. There's no X bars, no sample means. In this section, it's all about proportions. So we're talking about P hat, Q hat. So back to binomial things where there's two outcomes. So with this section, when we're going to find our critical value, we will be using inverse norm to find our critical value, but we are using P hats and Q hats. So this is a proportion section. So the first thing we got to start with is that population symbol that we're after. We know when we're talking about means, we're going from sample mean to population mean. For a proportion, we are going from a sample proportion. This is a sample proportion when you have a P hat on it. And we are trying to get to a population proportion, which is just a P, no hat. So our point estimate for proportions is P hat. So it is taking your X divided by your N. So X is like the number of successes, what you're measuring, divided by your total sample size. Or you can think of it as the small one over the big one. This is your ratio that's being given to you. So it might say 7 out of 10 people like Facebook. It would be 7 divided by 10. It's always the smaller one divided by the bigger one. That's your X over N. And then in order to find Q, which we'll need later for our formula, Q is always then your failures. So 1 minus P will give you your Q. So here's our first example. In a survey of 1,550 US adults, 1,054 said that they use social media website Facebook. Find a point estimate for the population proportion of US adults who use Facebook. So point estimate, means we're looking for p hat, x over n. So x is the number of successes. So the people that do like to use Facebook, so 1,054 over your total sample size, 1,550. When we divide that, we get 0.68. This is what they're after. That's your point estimate. Now, just as a heads up, because we'll need to find it in a minute, if we needed to know Q hat, it's 1 minus P hat. So 1 minus 0.68, we get 0.32. This would be Q hat if we needed to find it. Now we're going to go through all of our motions to get from the beginning all the way down to our confidence interval. You'll see little notation changes like this, where instead of X bar, we are using P hat, but it's the same confidence interval we want at the end, and your margin of error formula has updated. So we've got ZC, again, we're using inverse norm to find it, and you've got P hat and Q hat, you know how to find, and you'll be getting your sample size. So here are your steps. Identify the pieces in the problem, your X and N specifically to find P hat in case P hat is not given to you. Once you have it, before we get even farther into the problem, you do have to check your conditions. So in this case, in order to check conditions, it is your N times P hat and your N times Q hat. We need to make sure that both of those numbers are at least 5 or bigger. As long as they're 5 or bigger, we can approximate things with the normal distribution, which is allowing us to use inverse norm. So we have to check that before we get any farther. Most of the time, our numbers are so big with our sample size that we fly past that criterion and we're good to go. But technically, we need to check that every time just in case, particularly if your sample size is really small. Once we have that critical value, you've got your margin of error formula and then your confidence interval. So here's our first example. Use the data in example 1. We have our P hat is 0.68. Our sample size was 1,550. Our X was 1,054 to construct a 95% confidence interval for the population proportion of US adults who use Facebook. And just as a reminder, we also already found Q hat as 0.32. So that was from 1 minus P. So since we already have P, we're going to check our criteria or our conditions, either one. N times P hat needs to be greater than or equal to 5, and N times Q hat needs to be greater than or equal to 5. So our sample size N times our P, and I'm going to do the other one at the same time, our sample size times our Q. When you multiply these, if it's bigger than 5, I just give myself a little check mark. Bigger than 5, little check mark. That's all we need to do. As long as they are 5 or bigger, it doesn't matter what the numbers are. 5 or bigger, we're good to go. So little check mark reminds me I've checked it, I'm good to go. So then our next step is our critical value. So our confidence is 95%. That's 0.95. So same as before, 1 half, 1 minus C. This is to find that area that we're going to plug into our inverse norm. And we get plus or minus 1.96. This is our critical value. Step 2, find that margin of error. Make sure when you are writing it, that square root should extend around the entire fraction there. So we're going to plug in our positive critical value. And then both our P hat and Q hat multiplied on top, divided by our full sample size underneath that radical. Try to do that step all at once. So you just type it all in, you click enter, and you get 0.0232. That's your margin of error. And your last step is adding and subtracting that from our p-hat. So 0.68 minus and plus margin of error. This is your confidence interval. And keep in mind with proportions, our p-values, they're only going to be between 0 and 1. They're going to be decimal values. They will be positive values. Same should be true for your final answer. These are still going to be very small numbers because we're estimating p. So it'll be small. It'll be between 0 and 1. These will be positive. Let's try it again. So this one says the figure below is from a survey of 800 U.S. adults ages 18 to 29. Construct a 99% confidence interval for the population proportion of 18 to 29-year-olds who got their news on the television. So if we look in our chart for television, this is our p-hat right here, 27%, and we have our sample size of 800. That's the only 3 things we need to do this problem. So I'm going to switch it to the next slide so we have a little bit more space. So again, we had a sample size of 800, confidence of 99, and our p-hat was 0.27. So first thing I'm going to do is find q-hat here. 1 minus p-hat. So we get q-hat is 0.73. So let's check our criteria or our conditions. N times p-hat and n times q-hat. Make sure our samples are big enough. So 800 times 0.27 gives us 216, bigger than 5, so we're good to go there. And then 800 times 0.73, again, bigger than 5, we're good to go. So first step is our critical value. Confidence is 99%, which we've already switched to 0.99. Plug it into our formula to find that area under the left curve, left tail, 0.005. We'll plug that into inverse norm, 0.005 for area. And we get ZC is both positive and negative, 2.5758. That is your critical value. Step 2 is margin of error. Let's plug in the positive of our critical value, always positive. Our p-hat and our q-hat multiplied over n. Round this off to 4 decimals, we get 0.0404. This is your margin of error. And last step, find your confidence interval, add or subtract that from your p-hat, your sample proportion. Point. 0.2296, 0.3104. That is your confidence interval. Now the last thing we have to cover is finding a minimum sample size. We've done this before with a z-distribution when we had means and standard deviations. Now we are doing it when we have a proportion and we're trying to find that minimum sample size. So keep in mind, if your answer from the formula is not a whole number, you will always round up to the next whole number. This formula also assumes you have a p-hat and a q-hat. So if you do not have a p-hat and q-hat, which is called a preliminary estimate, if you do not have that, then you will use 0.5 and 0.5. So a 50-50 between the two groups of success and failure, like flipping a coin. So if they don't give you a p-hat, use 0.5. If they do, use whatever they give you. And again, they'll give you a confidence so you can find critical value, and they will give you margin of error. The clue for margin of error is look for the term within, and it's right after that. So here's our last example. We're going to do it twice, one with a preliminary and one without a preliminary estimate. So it says you are running a political campaign and wish to estimate with 95% confidence the proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of the true population. Find the minimum sample size needed when, for this first scenario, no preliminary estimate is available. So that means we're going to do 0.5 for P and 0.5 for Q. So we've got our confidence, 95%. We can switch that to a decimal, plug it into our 1/2, 1 minus C, get 0.025, which we plug into inverse norm for area. And we get both positive and negative 1.9600 for critical value. So we can plug in everything we have into our formula to find our minimum sample size. We have 0.5 times 0.5 times the positive critical value over E, which there's your clue word, within 3%. Make sure you switch it to a decimal. So whatever that percent is, you switch it to a decimal. Don't forget the square in the back. We get 1067.1 repeating for our decimal, and we need to round it up. So we get 1068. Now the only thing we're going to change is I'm going to keep all the other numbers the same. I am going to change that to be a given preliminary estimate of 0.31. So if that's the case, Q hat then 1 minus 0.31 would give us 0.69. Everything else is the same. So our same critical value from the previous slide, same margin of error, 0.03. Again, it's coming from that 3% switch to a decimal. And let's see how that changes our answer. So minimum sample size formula, our new P and Q. Try to type all of this in at once and click enter. And we get 913 and some decimals, rounding it up to 914 for our final answer.